Let me start. So please pay attention to this very good lecture, because you will have all the stuff which you have studied so far, like from lecture 1 to lecture 6. So we'll do one example, and we'll go through all the steps. So this video is very important, so you will understand all the steps. So that's why I decided to record it for you. It will help you in your exam, and it will help you to understand all the concepts which we have studied so far. So if you remember that we started from, let me write the first step. We started from the frame transformation, right? That was our introductory lectures on frame transformation. I think we spent 2 lectures on this, and that was very important to understand the robotics. So in that we studied the rotation matrices, displacement vectors, and you know that we followed J. Gregg book's convention, right? I think chapter number 2. So we'll use this. I will not teach you frame transformation today, but we will go through the how to use them in this example today. So after that, we studied that how we can derive the kinematic diagram for a 2 degree of freedom planar manipulator, and did some examples, and derived the forward kinematics, inverse kinematics for that examples. So first we studied 1 link manipulator, then 2 link manipulator, and also I think the 3 link manipulators, both with revolute joints and prismatic joints. And the last 2 lectures we studied this differential forward kinematic, and then in which we applied, we studied the converted Jacobian matrix, because the Jacobian matrix is a matrix which will give you the relationship between what? Nafiz? Daniel?
Jacobian matrix is basically when we want to transform when we're doing the forward kinematics, differential kinematics, because the partial derivative is Jacobian to convert one to another.
So Jacobian matrix gave you the relationship between the velocity of the anti-factor and the velocity of your joints, right? And okay, this inverse differential kinematic we did not study last time, so let me cover it today. So these are the topics we have covered so far before the midterm, right? So after midterm, I will tell you what we study, but this is so far what we are studying. So we'll go through one example, and we applied all these steps to that example, so that you understand all the steps, right? So this I decided to give you apply all the steps to one example. So let's go through a brief introduction. What we have studied so far for what is forward kinematic, inverse kinematic. I will not go in detail, but you already know this one. So forward kinematic gave you the relationship between your joint space variables and your Cartesian space variables. So Cartesian space variables basically are your position and orientation of your anti-factor with respect to the base frame, and joint space variables are your joint variables, whether they are prismatic joints or revolute joints, and there can be any number of joints, 1, 2, 3, 4, 5, 6, depending on how we construct our manipulator. And inverse kinematic is the inverse relation, where we have the position of the anti-factor, and then we can represent it like this. So we have the Q is a joint variables, and we get this vector x. So x means that this whole vector x position, 3 position, 3 angular velocities, three angles, right? And this is for kinematic. So inverse kinematic, we can say that we know the Cartesian space parameters, and we apply some function, and then we get the joint angles, joint variables. So this is inverse kinematic, right? So we have studied it in very much detail in the last lecture. So today just I gave you just remind you what you have studied. And differential kinematic is the relationship between the velocities. Okay. So forward differential kinematic means that we have the q dot derivative of the angles, joint variables, and we derive some function, and we get the velocity affinity vector. The velocity affinity vector means that the linear velocity and angular velocity. So here it means that x dot, y dot, z dot, alpha dot, beta dot, and gamma dot. And inverse differential kinematic means that we write the differential here. So you know the velocity of your anti vector, okay, with this vector, and you apply some function, and you get the joint velocity. So this is just a review that we have done so far. So ultimately, in your velocity relationship, you end up with the Jacobian matrix, which will give you a relationship between your joint velocities and your anti-vector velocities. So we'll do this today through some example. So I made this example for you. So this example is very good because that it has a revolute joint R, and it has one prismatic joint P, okay, and it is simplified like 2 degree of freedom planar, 2 degree of freedom because it works only 2 dimension, planar x and y coordinate, x and y coordinates only, and this RP means that it has one revolute joint and one prismatic joint. So we'll take this example and we'll go through all the steps. So what is the first step? First step is that you draw the kinematic diagram, right? So what is kinematic diagram? That you have some physical robot or some picture of the robot, and then you draw the drawing of that robot on your paper, okay? And you should follow some rules that what it should look like. So we say that for the revolute joint, we use this kind of circle if it is 2D. If it is 3D, you can use this kind of cylinder for revolute joints, okay? And for prismatic joint, if it is like 2D, you can just show like this, or if it is 3D, you can show like a cube, okay? And then the direction of the motion you can show like this, or if it is moving upward, you can show a plate like this. Okay, this is the drawing rules, right? And one thing you said that the kinematic diagram we draw at a home position. What is home position? These are the questions I will ask you in the exam.
It's basically when all the joints are zeroed out.
Yes, so like I gave you example, like a human, what is our home position of arm? Like this. This is our home position, right? This angle 0, this angle 0. So if you want to do something, we go do something and then again home position. So similarly for every robotic arm and we design, we define some home position first. That in the when it is not working, where it should be. It should be like this, it should be like this, it should be like this, it should be like this. So it depends on how we define it. So let's define the home position like this, that this arm, this revolute joint is going in this way and this is this way. So this is actually 0 position, right? So we say that the angle is 0 and if it is a prismatic joint, then D is 0. And then for the analysis, for analysis purpose, analysis means what? We want to derive the forward kinematic, inverse kinematic, differential kinematic like this. Then we change the angles, right? So it is, we move our robot to non-home position, meaning there is some angle, there is some D, and so on. Because we want to do some analysis on this problem. And other thing is that we said that we have to draw the frames frames on every joint and also at the end effector. So this is what the kinematic diagram means, right? So here we have only 2 joints. Nafis, how many joints?
We have 2 joints.
Which one?
The first one is the revolute joint.
Mm-hmm.
The second one is prismatic.
Prismatic joint. So this linear joint, it can move up and down like this, okay, and this is revolute joint which can rotate like this. So we have two joints. Then let me increase the, okay. So first step is to draw the frames on every kinematic, on every joint. So this is our zeroth frame, where zeroth frame is attached to the ground, fixed on the ground, right? And then so it will not move. X0, Y0 will not move, right? But also we attach the first joint to our frame, first frame to our first joint, that is X1, Y1. So this X1, Y1 is a frame, a coordinate frame which is attached to joint 1, which is a revolute joint, right? And similarly, to the second joint. So what is the rule we said? What is the rule to when you attach a frame? Do you remember? First we fix the z-axis. No. Z-axis should be in the direction of motion. This is our first step. First we decide about the z-axis. Direction of motion or rotation, right? If it is prismatic joint, a revolute joint, a prismatic. So direction of motion means that z-axis should be, because this joint is moving in this direction, right? So this should be z-axis, and this frame is rotating about the frame which is out towards you, the axis towards you. So that angle is that axis is z-axis, right? So z0 is not 0. Z0, Z1 both. Z0 and Z1 both are out of plane or out of page, right? This you understand. We are studying on the planar robot, so our z-axis in case of the revolute joint will be out of the towards you, right? Out of the page. But z-axis of the this prismatic joint depend on what is the direction of our prismatic joint. If our prismatic joint is moving from left to right, for example, this is our prismatic joint. Let's say this is just a give example, right? So if our prismatic joint is moving in this direction, right? So that will be our z-axis. If our prismatic joint is moving upward, like this, then that will be our z-axis. If it is moving, let's say, any other direction, whatever, let's say it is moving towards you, then that will be z-axis. So depending on what is the direction of motion of the prismatic joint. So in our example, our prismatic joint is moving in this direction. So that will be our z-axis. What is z-axis? This is x1, so this will be x2, z2, 2 frame, right? First we decide as z-axis, or done. Then second is the x-axis. So x-axis will move, can go this direction, can go this direction. It cannot go this direction. Can that x go this direction? Can we write the x-axis on this direction?
No, because we want to have a program on
Yeah, we need a right angle, right? Axis. This is already z-axis, right? So we cannot write x-axis in this direction. So then, what are other options? It can go this direction, it can go this direction, right? So we can choose any. Let's say whatever you like. Okay, let you like this one. Okay. So that will be x2. Then how we determine the y-axis?
Rotation y-axis is 0. Right hand rule.
Right hand rule. We determine the direction of the y-axis through right hand rule. So, what is right hand rule? This one. If this is your z-axis, this is your x-axis, that will be your y-axis. Okay. Yeah. So, if you have like this one, this is your. So, it will be like this. So, this is your z2, this is your x2. So, that will be your. If I look from my direction, so it will be into the page. That will be y2. But here we are not considering the 3D case, so we don't need y2 actually. But let's see. In general, it will be y2 will be in this direction. And then at the last frame, which is our end effector, we also attach a coordinate frame because we have to deal with it. But that direction is same as the previous one. Keep the last frame direction as the previous one. That is our convention, right? So this is yes, please. So this completes our kinematic diagram, but still we have to do something. What? We have to attach. So first thing is that this is L1, direction from here to here, not direction. The distance from here to here, L1, and second is that let's see. This variable, we have to decide the joint variable. We have not decided yet. So first we are on the base frame x0 y0, and then also x1 y1 on the same location, and it is rotating about the z-axis. So what will be our first joint variable? Okay, it should be theta, but what will attach the subscript? Why?
Because it is rotating in relation to the significant.
No, but I told the rule how we attach the subscript. Subscript, this is very important. Subscript of joint variable.
We use the same subscript as the axis.
X next frame.
Yeah, yes.
We use the subscript which is the number of the next frame, because when this theta will move, which will affect the motion of x2 frame. It will not affect the other, or it will affect the others also, but it will immediate effect will be on the x2 frame. So we choose the subscript of the next frame, immediate next frame. So that's why we attach theta 2, not theta 1. Okay, it will affect the next frame. How we choose this joint variable? D, because it is prismatic linear. What will be the subscript?
D3.
D3, because when it is moved, the next frame will move upward, right? So this completes our kinematic diagram. We have attached the frames. Okay, let me write the steps. Maybe here. So for our kinematic diagram, there are maybe 2 or 3 steps. So what? First, draw the robot kinematic diagram and drawing in non-home position. Right? This is the first step. Because you are going to analyze the forward kinematic, inverse kinematic like this. Second, attach frames. Attach frames to what? To each joint. Right? What is third?
Attach variables.
Joint variables. Yes, attach joint variables to each joint, right? And also write the link lengths, write the link lengths, yes.
Can I come out for a minute?
Yes, sure. So link length, right? So this maybe 4 steps will complete your kinematic diagram. This is a very, very important step, because whenever you do anything with the arm robots, your kinematic diagram should be correct. If your first step is wrong, the next step will be also be wrong. Your forward kinematic will be wrong, inverse kinematic will be wrong, if your kinematic diagram has errors. So these 4 steps are very, very important to analyze any robotic arm. So we have done this for this simple example that we have attached the joint variables, we have attached the frames, link length L1, and then we attach the, okay, at non-home position we have done this. So I think this is complete right now. So our first step is done, draw the kinematic diagram. Next step, derive the forward kinematic model. We have done, and then we use this kinematic diagram to make our forward kinematic model. So we'll use the HTM approach, homogeneous transformation, matrix approach, right? So using homogeneous transform matrix. So how many HTM we need in this example?
1. Well, the thing is, 1 for the first row. Yeah.
So okay.
And then for the second one, we need also 1. So we have 2 HTMs and 1 for the final one.
First thing, what is our HTM? We have how many number of frames? 0, 1, 2, and 3. We have 3 frames, right? So what we need? We need our HTM finally 3 to 0, right? This is our final.
If you include trivial ones, yes.
Yeah, if we need 3 to 0, because 3 is our anti-factor. This is our anti-factor frame, and 0 is our base frame. So 0 is our base frame, right? So we want to go from 3 anti-factor frame to the 0 frame. So it means that we'll come back from 3 to 2, then 2 to 1, then 1 to 0, and that will make our 3 to 0. So we need 3 homogeneous transformation matrix, and it is clear from the kinematic diagram because first homogeneous will give you relationship between the frame 1 and 0. Second will give you relationship between 2 and 1. And third will give you relationship between 3 and 2. So we have, let me, if it is not mess up our drawing. Okay. So this one, first, 3 to 2. Second, 2 to 1, and third, here we have same origin, so that will give us 1 to 0. So we derive these 3 homogeneous transformation matrices, multiply them in reverse order, we get the final homogeneous transformation matrix. That is our forward kinematic. Forward kinematic means simply that, forward kinematic means that in simple words, that find, okay, that is find final HTM between, I write between like this, between anti-factor frame and base frame. So this is the meaning of forward kinematic, because if you find this HTM, final HTM between the anti-factor frame and the base frame, so what are basically you get? You get the rotation matrix between the anti-factor and base frame, you get the displacement vector between the anti-factor and base frame. That is what you need. That is your forward kinematic model, right? So here, for this example, we'll do step by step and try to find this this is 3 to 0 HTM. So we have studied this whole process, how to get this homogeneous transformation matrix, but I will not go in detail. Just for review, I put it here, the rotation matrices, but mostly we'll use this one, rotation about the z-axis. because rotation about z axis, we are dealing with the planar robot. So, if your robot is planar, so it means that our rotation is always about the z axis. So we use this rotation matrix. So, what is the definition of our HTM? Let us say we find HTM 1 to 0. It has the rotation matrix 1 to 0, it has displacement vector 1 to 0, and then we have some zeros, 3 zeros over here, and then the last setting 1. This is very general, right? General notation.
So what about prismatic joint?
Yeah.
We don't have any rotation.
Yes, we'll do it. We'll do it. So, prismatic joint is related with the HTM between 2 to 1, or maybe 3 to 2. We will see it one by one. So, first we go from 1 to 0. Okay, this is a review, just between two frames that we have frame 0, frame 1, and then what is meaning of this HTM, meaning that 1 to 0, meaning that you want to find this one, rotation matrix between frame 1 and 0, and displacement between 1 and 0, and then there is 3 zeros, and then there is 1. So, this is the picture, right? You have like this. So, what is meaning of this D1 to 0? It is a displacement vector, position vector and displacement vector, which is pointing to the origin of frame 1 and starting from origin of frame 0, right? With the position vector like this. So, we have to find what is that, and also what is rotation matrix? Rotation matrix is rotation between frame 1 and frame 0, when frame 1 is rotated by some angle theta with respect to frame 0. So, this will always be like in this case, in planar robots, this will be about the rotation about the z axis by an angle of theta. So, this we already have seen that cosine of theta minus sine of theta, sine of theta, cosine of theta, right, and then 0, 0 and 0, 0, 1. That will always be like this. This one, right? And displacement vector depend on your robot. Let's see, we would find for this example. So, first, okay, I think I have to go by one. Let me go down first. Okay, I will do one by one. Okay, so we start from 0, frame 0 and frame 1. Let's write, or you can say derive HTM 1 to 0. So, for that what we need? We need a rotation matrix and displacement. So, what will be the, well, let me first talk about this one. You see frame 1 and 0 on this picture, in this diagram. Frame 1 is here, frame 0 is here. What will be displacement? 0. There is no displacement because they are on the same origin. Two frames are on the same location. So, the displacement vector will be 0. So, it's easy. You can write, in general, you can write 3 zeros, but actually if it is two dimension, it is 2 zeros. But let us talk about in general 3 dimension. And what will be the rotation matrix between frame 0 and frame 1?
It will also be 0 because we don't have any rotation.
We have rotation.
No,
We have rotation theta 2.
So,
And rotation about the z axis.
yeah, cosine theta.
So, we will use this one with theta 2, right? And then our rotation 1 to 0 will be basically 1 to 0 about the z axis by an angle of what? Theta 2. So, it will be like just you see cos of theta 2 minus sine of theta 2, sine of theta 2, cosine of theta 2, 0, 0 and 0, 0, 1. That is it. You find the HTM between frame 1 and 0, right? Let us go for the second. Now, we find 2 to 1. So 2 to 1 will comprise of 2, this rotation matrix, this displacement vector, and 3 zeros and 1. That is our 2 to 1. So let's see our example, our kinematic diagram. So we have frame 1 over here, frame 2 over here, right? And displacement is L1. Let me draw it over here for you. So to make it simplify, you understand the. So we have, I think we have this one x1 in this direction, y1 here, and then we have x2 in this direction, and z2 in this direction, and this length is L1, and our according to right hand rule, our y-axis will be into the page y2, and this y-axis will be this z-axis will be out of the page z1, right? This is our in general 3 axis. So this is our frame 1 and frame 2. I redraw it. This is frame 1, this is frame 2, right? I redraw over here. Now easy to see. First, let's see D2 to 1. What is the meaning of this D2 to 1?
Displacement of origin of basis along the basis line.
Yes, this is a displacement vector which is pointing to this origin, which is frame 2, and starting from the origin of frame 1. So this vector actually basically, right? So this vector has 3 components in general: x component, y component, and z component, meaning that 2 to 1, y 2 to 1, z 2 to 1. What will be the x component? There is no theta 2 here. X component means that this vector in the direction of x1, and this vector in the direction of y1, this vector in the direction of z1. There are 3 components. So this component, this vector has only one component in the direction of x1, which is L1. In y1 direction it is 0, in z1 direction it is 0.
Why 0?
Why 0? Because, okay, because this vector, right? Okay. Let me explain over here. In general, if you have this vector, this one, this vector, let's say this is x1, y1, this is a vector, let's say L1, for example. So what do you say? It has 2 components, one in the direction of x1, one in the direction of y1, right? But if I say that your vector is only going in this direction, L1, so then L1 has component only in the x direction, x1 direction. In y1 direction it is 0. That is the vector, right? Vector has no component in the y1 direction. So same in here. This vector L1, this vector, whatever, what is the name of vector? Let's say vector O to whatever, O to B. So vector O to B, vector OB has only x component, which is equal to L1. Y component is 0 because there is no y component, there is no z component. So this is the full vector D1 to 0. We call it D2 to 1. Not vector OB. OB means that OB is equal to D2 to 1 vector. So this vector has 3 components. Only x component is L1, y component is 0, z component. Clear? And any question from this?
I have a question.
Yes.
What if we have like angle joint, not the joint, but just slightly angled L1?
Then we have.
Fixed angle, how it would look
So
like?
if for example this one, this example, if there is some angle, right?
Yeah, fixed angle, not theta.
Fixed angle, let's say you call it anything, alpha, and you can say 10 degree, right, whatever. So then it will be 2 components. X component of L1 will be, x component of this, let's say OB vector, right?
Yeah, it will be.
OB vector.
The problem is like we have z axis and y axis switched for our like next
So
pieces.
see, this is our, in this example, this is our x1 vector,
Okay.
one axis, y axis, and z axis, for example, like this, right? And our vector OB is only in this direction.
Yeah, but we have now slightly fixed angle upwards.
If we have angle, then it has to, it depends on if it had an angle in this direction.
So what would be like z to 1?
So if it is in this direction, for example, right? So if it is in this plane, then we have component only this direction and this direction. This direction again 0. But in general, if we have like this,
It will be 2 angles.
then we have 3 components. One component will go in the x-axis, one component will go in y-axis, one component will go in z-axis. It's just a vector. Vector you can revise your.
Okay, so if it was like a slight angle of 10 degrees,
Yes.
the second basis would be non-zero.
This will be non-zero, but this depends on third. If it is in this plane,
Yeah.
only 2 components. But if it is in general 3 plane,
Yeah.
then we have 3 components.
Okay.
This is vector, right? So in this case, our vector is going only in the x1 direction. There is no component in the y1 direction. There is no component in z. If it go like this, right, as you said, like this, then it will have 2 components, x1, y1 components. But z component again 0. But if it is out of plane, it is in if it is here, out of plane. So one component is z axis, one is y axis, one is y axis. Okay, so then we find the displacement vector. What about the rotation matrix? R2 to 1. In case of the frame, let's see this diagram. We have x1, y1, z1, okay, and x2, y2, z2. These are our two frames. What is the rotation matrix between these 2 frames? There is no angle.
It's along x-axis.
Okay, this is tricky. Let me make you easy for you. First I go down. So rotation matrix, if you have the, as I said, that if you have 2 frames like this, let me talk about x2, z2, and other frame is like some angle. Let's say this one x1, and let's say y1, or whatever, let's say z1. So what is the angle between them? This theta. So in this case, you find the rotation matrices based on these formulas, right? But what if the angle will become 90? Okay.
Well, instead of cosine, we'll have 1.
So
instead
yeah,
of cosine.
if your x-axis goes here, z-axis goes here, still we have angle, but now angle is 90, right? Again we can rotate 90 more. Again theta can be 90, can be 180, can be 270, can be 360, right? Or can be 0. In this case, if angle 2 frames are rotated like this, 2 frames have the angle 0, 90, 180, 270, 360 like this, then the rotation matrix becomes very easy to calculate. How? Let me tell you. You don't need to use these formulas in that case. This formula is general if your angle is theta, any theta, right? But the easy way to use this in this situation, if your angles are like this, then you just look at your frames. How your frames will look like? Okay, let me redraw over here. Maybe I go here. Okay. So let me redraw here. Your x1 is here, not x1 is here. Sorry. So your x1 is going in this direction, and y1 is going in this direction, and z1 is going like out of the page. Please see it carefully because this is very important. You will use this in many times in your next classes as well. And what is your second frame? x2 in this direction, z2 and y2 is into the page. So second frame is here, like here, and its second frame is x2 is in this direction, z2 is in this direction, and your y2 is in this direction. This is your situation, right? This is your frame like this, and this distance is L1. So if you, how to find the rotation matrix? We already found the displacement, right? No problem, L1, 0, 0. What is about the rotation matrix? So in this case, you know that your angles are at 90. Now your frame 2 is rotated by 90, not some angle.
Just without the x-axis.
So because this is this direction, this direction, it is they have some relationship between the 180 or 180 or 90 or 360 or 270 degrees. So in that case, this situation, you how to calculate the rotation matrix between 2 to 1. You just consider it like this. So x1 in the direction is same direction as the x2. We got this x1, this is x2, is no problem. What is the direction of y1? Y1 is in the same direction as what? This is y1. Y1 is same direction as z2. Right? Y1 is same direction as z2. What is z1? Z1 direction is opposite to y2, minus y2. If frames are rotated by 0 degree, 90, 180, 270, 360, you can use this method to find the rotation matrix. This is much more easier, as that you first consider which frame is rotated, which direction, 90 angle, then again 90 angle, then 180 angle. You use 3 rotation matrices, then multiply them, and then finally find the final rotation matrix. So this is a shortcut method, easy method to calculate the rotation between two frames. So first you decide, this is your, let's say you can, this is a rotated frame, your frame 2 is rotated with respect to frame 1, and let's say this is your fixed frame, previous frame. So if this is the situation, this is the condition scenario, so you write the directions first. x1 is in the same direction as x2, y1 is the same direction as z2, z1 is the same direction as minus y2. Clear? Not clear? Because this is plus y2 and opposite will be minus y2. There are 3 axes, right? Not rotated. When you have the axis like this, right? If you say this is z axis, this is what is this? Minus z axis, right? If this is your x axis, this is your minus x axis. If your plus y axis, this is your minus y axis. So
they switch positions?
3 axes, not switch position. When you draw the Cartesian coordinates like this, they also have the plus axis and minus axis. Then it clear?
Yeah.
So it is not like I think you should revise your matrices from your school book, matrices from maths. Very important. When you study robotics, matrices, vectors, algebra, that you should know. You should clear understanding. So vectors and matrices, right? So 3D Cartesian coordinate system has positive x-axis and negative x-axis. Positive y-axis, negative y-axis. Positive z-axis, negative z-axis. So in this case, if it is plus y2 axis, that will be minus y-axis. If it is plus z2 axis, that direction will be minus z2 axis. And if it is plus 2 axis, that will be the minus x2 axis. We don't write the plus, just we say, okay, if it is nothing, it means plus. So that is the case, right? We have frame, first frame fixed, let's say fixed frame, and second frame is rotated frame, then we have this relationship between directions of these two. Okay. After that, what? From this relationship, you can write in the matrix form. Let me write in matrix form. Then what you get? You can write these 3 equations, equation 1, let me call equation 1, 2, and 3. Write 1, 2, 3 equations in matrix form. So how you write it? x1, y1, z1, x2, y2, z2. Okay, what will be here? First component of this matrix. x1 is equal to x2, right? So it will be first component will be 1, 0, second component 0, this 0. So maybe I can write you in the full form. So full form is that x1 is equal to 1 x2 plus 0 y2 plus 0 z2. That is the full form. And y1 is equal to 0 x2 plus 0 y2 plus 1 z2, right? And z1 is equal to 0 x2 minus y2, good, and plus 0 z. This is the full form, but I just use short notation. So now you can write this in the matrix form, right? So second will be 0, 0, 1, and third will be 0, minus 1, 0. That is the rotation matrix. Yes, please. This is the rotation matrix between two frames, R2 to 1. This is much easier method if the frames are rotated by 0 degree, 90 degree, 270, like this. Okay, so always use this kind of notation. So now you find your rotation matrix. Okay, you got a rotation matrix R2 to 1, and displacement vector already you got. So you can build HTM 2 to 1. Clear? That will be R2 to 1, D2 to 1, 3 zeros, and that is the one. So we have done. Okay, I think it is break time. So we'll stop here, and after break we'll start again this example. And please come after 10 minutes.